Section 6.2.9 Generator Expressions. The grammar shows it's just like a list comprehension, but with parens instead of square brackets. A generator expression yields a generator object, a lazy iterator that produces values one at a time. 3 things to know. The leftmost iterable expression is evaluated immediately when the generator is defined, not lazily. That's an important subtlety. Parentheses can be omitted when the generator is the sole argument in a function call, so sum x for x in range 10 doesn't need double parens, and yield from are prohibited inside generator expressions since Python 3.8. Generator expressions in practice. Line 1. Squares gen equals x squared for x in range 1 to 6 in parens. That gives us a generator object, not a list. Line 3. Next squares gen gives 1. Line 4. Next again gives 4. Line 6. A for loop consumes the rest. Line 7. Print val gives 9, 16, 25 on separate lines. 2 key insights. Lazy. Values are produced on demand, never all in memory at once. That's the whole point. And one shot, once a generator is exhausted, it's done. You can't rewind it. If you need to iterate again, create a new generator. Section 6.210. Yield expressions. Line 1 shows the grammar. Yield followed by a yield list, or yield from followed by an expression. 2 forms, 2 use cases. Left column, generator function. Using yield in a function body makes it a generator function. Calling it doesn't run the body. It returns a generator iterator. The body only runs when you call next. Right column, async generator function. Using yield inside async def makes it an asynchronous generator function. And a restriction, yield expressions are not permitted inside comprehensions or generator expression scopes since Python 3.8. Simple generator function. Line 1. Def countdown takes n. Line 2. While n is greater than 0. Line 3. Yield n. Execution pauses here and hands n back to the caller. Line 4. N minus equals 1. Then the loop continues. Line 6. Gen equals countdown 3. Nothing runs yet. We just have a generator object. Line 7. Next gen resumes the body, hits yield 3, pauses, returns 3. Line 8. Next again yields 2. Line 9. Next again yields 1. 2 key points. The body only runs when next is called, not when the function is called. And yield pauses execution, saving all local state, the value of n, the instruction pointer, everything, until the next call. This diagram shows the generator life cycle in 4 steps. Step 1. Call. You call the generator function. This creates the generator object instance, but runs 0 lines of the body. Step 2. Next or send. You call next or send on the generator. Execution resumes from where it was suspended. Step 3. Yield. The generator hits a yield statement. It suspends execution and returns a value to the caller. Step 4. Close or stop iteration. When the function body finishes or hits a return statement, stop iteration is raised and the generator is exhausted. The key thing the description adds, all local state is retained across suspensions, variable bindings, the instruction pointer, the evaluation stack, exception state, everything. Generators are similar to coroutines, but always transfer control back to the caller at each yield. Generator objects expose 4 methods. Dunder next starts or resumes execution until the next yield. The current yield expression evaluates to none when resumed this way. Raises stop, iteration when the generator is exhausted. Send takes a value and resumes the generator, making that value the result of the current yield expression inside the generator. This is how you push data into a generator. Throw raises an exception at the point where the generator is paused. You can inject any exception type. And close injects a generator exit exception to shut the generator down cleanly. Since Python 3.13, close can also return a value if the generator returns 1 on exit. This is the canonical echo generator from the Python docs. Line 1. Def echo takes an optional value defaulting to none. Line 2. Outer try block wraps everything for the finally cleanup. Line 3. while true loops forever. Line 4, inner try to catch exceptions from throw. Line 5, value equals yield value. This is the two-way communication. We yield the current value out, and whatever comes back from send becomes the new value. Line 6, except catches any exception thrown in via throw. Line 7, value gets set to the exception object itself. Line 8, finally runs when close is called. Line 9, prints the cleanup message. Line 11, generator equals echo 1. Line 12, next gives us 1, the initial value. Line 13, print confirms 1. Line 14, send 2, resumes and injects 2, which becomes the new value. We get 2 back. Line 15, print confirms 2. Line 16, throw sends a type error with spam. The generator catches it and sets value to the exception object, then yields it back. Line 17, we see type error spam. Line 18, close triggers the finally block. Line 19, prints the cleanup message. Let's focus on dunder next specifically. Line 1, def squares takes n. Line 2, for I in range 1 to n plus 1. Line 3, yield I times I. Each call to next resumes here and returns the next square. Line 5, gen equals squares 3. Nothing runs yet. Line 6, next gen resumes the generator. I equals 1, yields 1. Line 7, next again, I equals 2, yields 4. Line 8, next again, I equals 3, yields 9. Line 9, next with a default of done. The generator is exhausted. Instead of raising stop iteration, we get done back. Line 10, next again with the same default. Still done, safe to call repeatedly. 3 rules. Next gen is shorthand for gen.dunder next and also accepts a default. Stop iteration is raised when the generator returns, and for loops catch it automatically. And next with a default is the clean way to avoid try, except when you just want a fallback value. Section 6.2.10.3. Async, generator functions. A yield inside an async def creates an asynchronous generator function. It returns an async iterator consumed with async for, not a regular for loop. 3 things to know. Finalization risk. If an async generator isn't resumed before garbage collection, pending finally clauses may not execute. That's a real gotcha. Event loop responsibility. The event loop must call a close and run the resulting coroutine to ensure cleanup happens. And there's a finalizer hook. You can register one via sys.set async-gen hooks. The asyncio event loop does this automatically. The caution box. Yield from is a syntax error inside async generator functions. Use async for instead. Async generator in practice. Line 1, import asyncio. Line 3, async def async countdown takes n. Line 4, while n is greater than 0. Line 5, await asyncio, sleep 0. This simulates async I/O. It suspends the coroutine and lets other tasks run. Line 6, yield n. We hand the current value back to the caller. Line 7, n minus equals 1. Line 9, async def main. Async generators have their own method set, 4 of them. Dunder next returns an awaitable that resumes the async generator. You await it to get the next value. Raises stop async. Iteration when exhausted. A send takes a value and sends it into the async generator. Must be called with none to start, just like sync generators. Athrow raises an exception at the pause point. Note, the second signature for athrow was deprecated in Python 3.12. And a close throws generator exit into the async generator to finalize it. Same pattern as sync generators, just with a wait in front of everything. Async generator methods in action. Line 1, import asyncio. Line 3, async def ticker takes n. Line 4, for I in range n. Line 5, await asyncio dot sleep 0 to simulate async I/O. Line 6, yield I. Line 8, async def main. Line 9, gen equals ticker 3. Line 10, await gen dot dunder annexed, gives the first value, 0. Line 11, print confirms, 0. Line 12, await dunder annexed again gives 1. Line 13, await dunder annexed again gives 2. Line 14, asyncio.run main runs it. 2 key rules. Use await gen dot dunder annexed or async 4, never plain next, which raises a type error on an async generator, and always await a close when abandoning a generator early to ensure cleanup code runs. Section 6.3, Primaries. We're moving into the most tightly binding operations in Python: attribute references, subscriptions, slicings, and calls. When Python evaluates a complex expression, it resolves primaries first, before any operator. Understanding this section explains why things like list.append, parent works the way it does. It's an attribute reference followed by a call, and both bind tighter than any arithmetic or comparison operator. Line 1 shows the grammar. A primary is either an atom, an attribute reference, a subscription, or a call. 3 icons break down the non-atom forms. Attribute reference, primary dot identifier. This calls dunder get attribute on the object. If that raises attribute error, Python falls back to dunder get attr. Subscription, primary in square brackets. This calls dunder getitem or dunder class getitem for class-level subscriptions like generics, and call, primary in parens with arguments. This invokes any callable object via dunder call. These 3 operations are the workhorses of Python code. Primaries with a simple dict. Line 1, data equals a dict with name and scores. Line 4, data.keys. That's an attribute reference. We access the keys method on the diked object. Print gives us diked keys with the 2 keys. Line 7, data square bracket name. That's a subscription, dunder getitem with the key name. We get Alice. Line 8, data square bracket scores square bracket 1, chained subscription. First we get the list, then we index into it to get 87. Line 11, len data square bracket scores. That's a call. Len is called with the scores list, giving us 3. Line 12, sorted with reverse equals true. Another call, giving scores in descending order. 3 rules. Attribute reference calls dunder get attribute, subscription calls dunder get item, and call invokes dunder call on any callable. Section 6.3.2.1, Slicings. A slice extracts a portion of a sequence using start : stop : step. Any part can be omitted. Missing values default to none, and the sequence fills them in with sensible defaults. Line 1, names is a list of 6 strings. Line 2, names square bracket. 1:3 gives indices, 1 and 2. Stop is exclusive, so index 3 is not included. Line 3, names with :2 gives every other element. Line 4, names square bracket : -3 gives everything except the last 3. The info box explains what's happening under the hood. Python constructs a slice object, slice, start, stop, step, and passes it to dunder getitem. You can build one of these explicitly, which we'll see in the exercise. Slicing in action on a list of 0 through 5. Line 1, s equals the list. Line 3, s square bracket, 1:4 gives 1, 2, 3. Stop is exclusive. Index 4 is not included. Line 4, s with :2 gives every other element, 0, 2, 4. Line 5, s with :-1 reverses the list, 5, 4, 3, 2, 1, 0. Line 6, s square bracket, (-2) gives everything except the last 2. Line 7, s square bracket, 2, gives everything from index 2 onward. Line 10, sl equals slice 1, 5, 2. We build the slice object explicitly. Line 11, s square bracket sl gives us 1 and 3, same as s square bracket 1, 5, 2. 3 rules. Stop is always exclusive. negative step reverses, and step cannot be 0 or you get a value error. And Python builds a slice object internally that gets passed to dunder getItem. You can build one explicitly too. 2 more subscription forms. Left column, comma separated subscripts. When you write primary square bracket 1, 2, 3, Python packages those into a tuple and passes that tuple to dunder getItem. The REPL example shows demo square bracket 1, 2, 3. The object receives the tuple 1, 2, 3. This is how NumPy multidimensional indexing works. Right column, starred subscripts added in Python 3.11 via PEP 646. A starred expression in a subscript is unpacked into a tuple. The REPL example shows demo square bracket star range 10. The object receives the tuple 0 through 9. The key point, the comma creates a tuple and dunder getItem receives that tuple. NumPy example for comma-separated subscripts. Line 1. Import numpy as npsars lines 4 through 6. Grid equals a 3x3 array. Line 8. Grid square bracket 1, 2 passes the tuple 1, 2 to dunder getItem. That's row 1, column 2, which is 6. Line 9. Grid square bracket 0, 0 gives us 1, top left corner. Line 12. Cols equals a list of 0 and 2. Line 13, grid square bracket 1, star cols. The starred subscript unpacks cols into the tuple, so we're selecting row 1, columns 0 and 2. We get 4 and 6. 2 key rules. Comma-separated subscripts like obj square bracket 1, 2 pass the tuple 1, 2 to dunder getItem, common in NumPy for multidimensional indexing. And the starred subscript syntax requires Python 3.11 or later. Use explicit tuples for older versions. Section 6.3.3. Calls. A call invokes a callable with positional and/or keyword arguments. All argument expressions are evaluated before the call. 4 arrow bullets cover the argument forms. Star expression unpacks an iterable as positional arguments, processed before keyword args. Double star expression unpacks a mapping as keyword arguments. Excess arguments. Excess positional args go to star identifier in the function signature. Excess keyword args go to double star identifier. And since Python 3.5, any number of star and double star unpackings are allowed in a single call. That's PEP 448. Calls in practice. Line 1. Def greet takes name and a default greeting of hello. Line 2. Print the formatted string. Line 5, greet Alice, hi. Positional args, gives hi Alice. Line 8, args equals a list of Bob and hey. Line 9, greet star args. The star unpacks the list as positional arguments, gives hey Bob. Line 12, quogs equals a dict with just greeting set to howdy. Line 13, greet Carol, double star quogs. The double star unpacks the dict as keyword arguments, gives howdy Carol. 2 key rules. Star unpacks iterables as positional args. Double star unpacks mappings as keyword args. And all argument expressions are fully evaluated before the callable is invoked. What does a call actually return? 4 cases. User-defined function. Executes the code block and returns whatever the return statement specifies, or none if there's no return. Built-in function or method. Result is determined by the interpreter, varies by function. Class object. Calling a class returns a new instance of that class. And class instance. If the instance defines dunder call, calling it has the same effect as calling that method. The common gotcha, forgetting that functions without an explicit return silently give you none. That's a frequent source of bugs. Return values in action. Line 2. Def add takes A and B. Line 3. Return a plus B. Line 5. Print add 3, 4. Gives 7. Explicit return. Line 8. Def say hi has no return statement. Line 9. It prints hi from inside. Line 11. Print say hi. This prints hi from inside the function, then prints none for the return value, because there's no return statement. Two joined boxes drive it home. No return statement means none, a common source of bugs, and an explicit return statement sends a value back to the caller immediately. Section 6.4. Await expressions. Line 1 shows the grammar. Await followed by a primary. Left column, what it does. It suspends execution of a coroutine on an awaitable object. Can only be used inside an async def function. Using it outside raises a syntax error. Right column, version info. Added in Python 3.5 as part of the native coroutine and async await syntax from PP 492. The info box lists what's awaitable: coroutines, objects with a dunder await method, and tasks and futures from Asyncio. Await in practice. Line 1, import Asyncio. Line 3, async def fetch data. Line 4, await Asyncio sleep. 1. Execution suspends here. The event loop can run other coroutines while we wait 1 second. Line 5, return data ready. Line 7, async def main. Line 8, print starting. Line 9, result equals await fetch data. We suspend main here until fetch data completes. Line 10, print the result. Line 12, asyncio.run main kicks off the event loop. Output, starting, then after a 1 second pause, data ready. 2 rules. Await only works inside async def. Using it outside is a syntax error. And you can await coroutines, Asyncio tasks, futures, or any object that defines dunder await. Now we're into the operators section, 6.5 through 6.9. Power, unary, binary arithmetic, shifting, and bitwise operations. These are the building blocks of numeric computation in Python. We'll go through each category with examples. Section 6.5, the power operator, double star. Line 1 shows the grammar. It's either an await expression or a primary, optionally followed by double star and an unary expression. 3 boxes. Binding. It binds more tightly than unary operators on its left, but less tightly than unary operators on its right. And it's right associative. So negative, 1 double star 2 equals -1, not 1. Behavior. It's the same as calling pow xy. A negative exponent on an integer gives a float result, so 10 double star -2 gives 0.01. Edge cases, 0.0 to a negative power raises 0 division error, and a negative base to a fractional power gives a complex number. Power operator examples. Line 2, 2 double star, 3 double star, 2. Right to left, 3 squared is 9, then 2 to the 9th is 512. Not 8 squared, which would be 64. Line 5, -2 double star 2 is -4. The minus applies after the exponentiation. Line 6, parent -2, parent double star 2 is 4. Parents force the negation first. Line 9, 10 double star -2 is 0.01. Negative exponent on an integer gives a float. 2 key rules. Double star chains right to left, so always use parentheses when stacking powers to be explicit. And the unary minus gotcha, -x double star n, applies the minus after the exponentiation, so wrap in parens to get the sign you expect. Section 6.6, unary operators. Line 1 shows the grammar. A unary expression is either a power expression or unary minus, unary plus, or tilde applied to another unary expression. 3 operators. -x, negation, calls dunder neg. Positive x, unchanged value, calls dunder pos. And tilde x, bitwise inversion. The formula is tilde x equals -x plus 1, all negated, or more simply, -x minus 1. So tilde 5 is -6, integers only, calls dunder invert. Unary operators on x equals 5. Line 4, -x gives -5, dunder neg. Line 7, positive x gives 5, no change, dunder pos. Line 10, tilde x gives -. 6, bitwise invert, -x minus 1. Line 11, tilde 0 gives -1. Line 12, tilde, negative 1 gives 0. Line 15, class my int with a custom value. Line 16, dunder init stores the value. Line 17, dunder neg returns a new myint with the negated value. Line 18, dunder invert returns a new myint with negative v plus 1, all negated, same formula as integers. Line 19, dunder repar for display. Line 21, n equals myint / 3. Line 22, negative n gives myint negative 3. Line 23, tilde n gives myint negative 4. 2 watchouts. Tilde is not a Boolean not. It flips every bit. Tilde 5 gives negative 6, not false. And positive x can surprise you. Dunderpos can be overridden to do something different from just returning the same value.